Hello my friends, so I've just got word that basically one of the speakers we use in our TED event, it's been a bit of a legal process, has been threatening to tell TED that our talks are a wind-up. And whilst they've been uploaded and we've got everything needed for our video, just in case our video goes up and this talk is no longer there, I wanted to provide some proof that it was and that it did go up, and if it does get taken down, it's a shame, but I'm not going to be extorted. I'm not going to let someone extort thousands and thousands of pounds out of me. But long story. But here is some proof. It is currently, what is the date? 6:25, Monday the 5th, 2022. It has a cool 2,000 views. It says, William Lenny is a nuclear physicist from Newcastle upon Tyne. And here is some comments. If I click on the thing, like it's on there. Anyway, if you're seeing this, that means it did get taken down, and here's a re-upload.
So, one of my favorite questions to ask people is, what would you do if you were sent 300, 400, 500 years into the past with nothing but your current knowledge? The majority say they would accelerate human development, right? Create technology and the internet, and stop all wars before Churchill is even born. But if I would ask most people how to make a light bulb or to create electricity out of nothing, you would realize just how complicated such feats really are. Electricity in general forms such an integral part of modern society, controlling everything from airplanes to your nervous system. And yet we generally rely on a few individuals to understand where it comes from and how to control it, with not giving much thought into what is actually going on inside the wires and circuit boards that dominate our life. Quantum physics, the study of such phenomena, offers the answers to this and so much more. And yet it's a field of science so full of mystery and so blatantly unintuitive that it scares away many of those who peek into the folds behind its great enigmas. But before we delve into its great complexities, let's take a look back to its humble beginnings as a subject of mere curiosity. 3,000 years ago, in ancient Greece, philosophers handling blocks of the expensive resin amber noted something peculiar. When rubbed, particulates of dust and fine dirt began to be attracted to its surface, as if some great force was acting between the two for a short space of time. The Greeks didn't realize it, but just like a child rubbing a balloon on their head and sticking it to their bedroom wall, they had discovered static electricity. Static electricity remained a mystery for centuries, being used rather as a party trick instead of having any significant basis within science. This changed around the 18th century, when Benjamin Franklin conducted his famous kite in a storm experiment, where, by nearly getting himself struck by lightning, he successfully proved that lightning and static electricity were indeed the same thing. By 1897, British physicist James Thomson had discovered a new particle, the electron, and pieces of this millennia-old puzzle began to fall into place. Electrons are fundamental particles, meaning they are not made up of anything else. They form the building blocks of atoms, and in turn, everything we experience in the universe. But the most special and relevant thing about them is that they have a charge, a negative charge. This is significant because particles with a charge like to move, and when they do, electricity is generated. In fact, the word electron comes from the word electricity, which is Latin for amber, taking us back all the way to where it began back in ancient Greece. And this is where quantum physics also began. Since its early days, in Greece, it has grown into a subject used as a tool to scare undergraduate physics students, and as a way for directors to explain their absurd time travel concepts in their movies. As Ant-Man said, do you guys just put quantum in front of everything? But while most people see quantum physics as a mess of equations that they could never hope to understand, its actual job is simply to see how small things move. Okay, so that's all well and good. But if all we need to do is understand how electrons move, then why is this subject so notoriously complicated? Well, this is where quantum mechanics and its big brother in classical physics differ. So if I show you a car, speeding down the motorway. It would not be difficult at all for you to tell me what lane the car is in, where it's going, or how fast it's going. No matter if you use complicated maths or just your eyes, you're always going to get the same result. This is great for the classical physicists like Newton. But when we look smaller, much smaller, things are no longer that easy. You may have heard of the famous thought experiment known as Schrödinger's cat. It states that if we have a cat in a sealed box and we place a device in that box that will kill the cat, we as an observer from outside of the box who can't see in can never know if that cat is alive or not. For all we're concerned, it's both. Now, this hypothetical situation is really just a way for physicists to say, we have no clue of what's going on inside that box, because in the box, our electrons are moving. And today, this is our big problem. Now, you're always going to have the guy that says, just take a look in the box, take the lid off and have a look inside. But when we do, with electrons, crazy things start to happen. For one, these particles appear to act as two completely different entities. A particle and a wave. So we've been calling these objects particles just because it's a bit easier, right, to deal with and visualize them. And a particle moves in a subatomic way, the same way a football moves in ours. It's a mass that moves in predictable ways from one place straight to another. This makes sense. An electron is usually pictured as a small sphere. But unfortunately, life isn't that simple because it also behaves as a wave. So, picture a pebble being dropped into a pond. It hits the surface and a wave is created, a disturbance in the water itself that radiates outwards from where the pebble is dropped. Now, this type of disturbance in water or in air is what we in physics describe as a wave. And half the time, this is what our particle decides to be. If we shoot individual particles through a slit and at a wall, one at a time, we see they act like a wave, hitting the wall in only a way that a wave would do. So what on earth is going on? Well, it seems that every single thing in the universe, at least on the quantum scale, acts like both a particle and a wave. In fact, even you and I can be proven to act like a wave at times, just an incredibly small one. So I calculated my own wavelength to be this, which is very, very small, but nevertheless still calculable. So, right, we've established that our electrons are particles, they're waves, and they're completely unintuitive, which isn't great. It's a lot of stuff at once, and it's quite confusing. But don't worry, it gets worse. Because let's go back to our car example, right? So imagine I asked you to tell me where the car was. It's pretty simple, right? You have a look, you could grab a street name or a coordinate. That would be pretty easy. Then imagine I ask you to tell me that same car's velocity. Again, with a basic calculation, you could tell me the answer. So what's the problem? Well, if we replace that car with an electron, things once again get horrendously complicated and strange. In 1927, Heisenberg discovered what we now know to be as the uncertainty principle, which states that you cannot possibly know a particle's position and velocity at the same time. In other words, if you know exactly where a particle is, you cannot possibly know how fast it is moving. To us, this makes no sense whatsoever. But in every experiment and calculation we've thrown at it, it's proven to be true 100% of the time. In other words, the movement of electrons is not quite as simple as they seem. So, we have successfully seen that particulates, like our electrons, don't behave in any way that makes sense to us intuitively. Now, to me, the most bizarre thing about all of this is that when it comes to quantum physics, this isn't even the most mind-boggling thing. Things get even weirder when we start to look at gravity. So if I was to ask you, right, what you think the strongest force constantly acting upon your body is, you would probably say gravity, right? Because gravity is what keeps you stuck to the Earth, and it's what keeps the Earth moving around the sun. Pretty powerful stuff. But it's not. In fact, when we delve back into our quantum world, we see two strange things about gravity. First of all, it's actually pretty weak, to the point that it's barely noticeable when acting between two electrons. This astoundingly powerful force that drags an object the size of the Earth tens of thousands of miles per hour through space can barely move a particle thousands of times smaller than an atom. Secondly, we have no idea how it works on such a small scale. All of the forces we observe acting in the quantum world are both much, much stronger than gravity and much easier to understand. In fact, we have detailed models and experiments that can explain those forces in incredibly precise detail. And yet gravity, the seemingly most obvious of them all, remains a mystery. We don't know where it comes from, we don't know what causes it, and we don't even know if it works the same everywhere. With such a mystery still to be uncovered, it remains possible that one day we may be able to harness the very cause of gravity and use it to manipulate space as we please. But for now, we are stuck in our seemingly ever-present mentality of I don't know. Quantum theory has been a vast field of study since its inception, nearly a century ago. But its counterintuitiveness, its mathematical mystery, and seemingly complete randomness has meant that it's a subject that's been mired with controversy. Indeed, Albert Einstein, who pioneered some of the early work on the subject, famously said, "God does not play dice with the universe." So, what's next? Well, there are thousands and thousands of theories about why particles appear to move randomly and as weirdly as they do. Everything from string theory to multiverses to other dimensions are being discussed daily in the scientific world. But as a subject, quantum theory is still in its infancy. Will we one day be able to harness this weirdness to create wormholes or teleportation or time travel? Probably not. But if you showed a scientist 100 years ago just some of the concepts we've talked about today, they would likely be just as suspicious of what the future holds. And that's why the most complex, convoluted, and controversial area of science is still, to this day, so misunderstood. Thank you very much.